Hi everyone. I know you are not able to do the lab today in person, but I'm going to make a video about how it works. So you need to know a few things about the background of water. So water is actually a cute little molecule that looks like a Mickey Mouse. And so if you look on the board here, water, which is an oxygen and two hydrogens, has two charges. The oxygen is negative and the hydrogens are positive. So if you take two of these Mickey Mouses, which I have these two models here, they will in fact actually stick together. You can see the white hydrogen is sticking to the red oxygen because one's positive and one's negative. That is called cohesion when water sticks to other water. So cohesion, water sticks to water. That's going to create something called surface tension. So if I have like a pond or a stream, when those waters are next to each other, they're all going to want to stick together. That's going to create some tension. That allows like little bugs or little lizards to walk or run across the water because the waters are sticking together. The other thing that water can do is called adhesion. So water can stick to other molecules. So if it rains and there's a leaf, the water is going to stick like in these little bubbles to the leaf. Or let's say you have a spider web. Those little Mickey Mouses are going to stick to the spider web, which is going to allow the spider to get water even after the fact. There's one other thing that water can do that's called capillary action, and that's when water is in tiny little tubes. It can actually go up against gravity, and that uses adhesion and cohesion together. So now we can get into the lab. So the first challenge is we are going to fill a Dixie cup all the way up with water. Okay, so this Dixie cup, if you can see how it's all the way to the brim. Okay? So when it's filled all the way to the brim, we need to predict how many of these paper clips can fit inside of the water. Okay, so you can see the water almost shaking a little bit because it's so high. So make a prediction on your lab as to how many can fit. So most kids, like today actually, most kids have said about 5 or 6. Okay, so you don't want the water to spill. So how many can fit without the water overflowing? So it actually turns out, so I just did 1, 2, 3, 4, 5, 6, 7, 8, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75. You can see the water actually shaking, but it's not spilling. It's actually creating a little bubble. And that's because the waters are piling up, okay, on top of the cup, but they won't spill over because when this water wants to leave, to fall, its buddies, because they're magnetized, right, because they're sticking to each other, its buddies are holding on to it. So it's creating either surface tension or cohesion on top of that bubble, which is kind of cool. So challenge number 2. So for challenge number 2, you need to get the water from this beaker into this beaker keeping the beakers about a foot apart, and the string has to be involved. Okay, so what I get a lot of people doing, they keep the beakers apart, they take the string, you got to get the string from here, the water from here over to here. I get a lot of students who will squeeze the string. So they'll take it, and they'll squeeze the water, and then they slowly try to get the water from this beaker to this beaker. It actually turns out, and you guys lucked out, you don't even have to figure this out, that if you do this with the string, you can keep the beakers 2 feet apart or a foot apart, and you can hold the string tight. So you actually really want to get the string really wet so that, because you know water sticks to water, but the water will also stick to the string, and it'll go nicely down the string into the other beaker. So the string is involved, the 2 beakers stay about a foot apart, and the water just sticks to the string. So that's actually called adhesion, when water sticks to the string, but it's also really technically cohesion because water is also sticking to the water on the string. So that is challenge 2. Challenge 3, I actually just have to pull up the lab real quick. Challenge 3 is the capillary tube. Okay, so the capillary tube is actually this little glass tube, and we're going to put it, not going to mess with the pressure or do anything weird with it, but what I'm going to do is I'm going to put the tube directly in. And if you look here, the blue water on the inside of the tube actually goes higher than the water on the inside. And that, again, has to do with the fact that the waters are going to stick to the sides of this tube because it has those charges that are going to allow it to stick. And this, again, is how plants are able to get water up their veins without sucking, right? They can't suck on a straw the way we do. And they're able to get water up. All right, so next challenge. Let's see. Sorry. So that was challenge 3. Have to move this. Challenge 4. So let's talk about the boiling point and freezing point of water. So the boiling point is between 95 and 105. So we all know that water boils at 100 degrees Celsius and it freezes at 0 degrees Celsius. So why is that good, that it spends most of its time as a liquid? Well, obviously we like that for our oceans and our rivers and our ponds and for drinking water and things like that. The other thing about water is you'll notice that it boils in Fahrenheit at 212. So you can see this graph here about salt. When you add salt, it actually has to be hotter to boil. So when I add 1 tablespoon of salt, it boils at 116 versus when I add 2 tablespoons of salt, it boils at almost 218 degrees Fahrenheit. So the reason we add salt is not to help it boil faster, it's just for flavor. It actually has to be hotter. All right, so now we have to compare alcohol to water. So what I have is some ethanol here. And ethanol is, this is the same stuff that's in beer and wine. Typically though in wine, you'd have only like 10 or 15%, in a beer, maybe 5%, even in vodka, maybe 40%. I'm trying to figure out how you can see this. This is actually 95% alcohol, so really, really strong. So what I'm going to do here is I'm going to take 2 pieces of paper, and on one of the pieces of paper, I'm going to put alcohol, an equal amount of alcohol, little paper towel. And on the other piece of paper, I'm going to put an equal amount of water. Okay, and so what I'm going to do is I'm going to rub this on the desk. Okay, and I'm going to try to show you. Let's see if we can see here. Let's see if I can make the recording bigger. Sorry, it's a little bumpy. Oh, so you can see here, the water stays behind because it's sticking to the table, it's sticking to its buddies, whereas this alcohol here is almost completely gone. Almost. And so it evaporates really quickly, and we see that in our cooking. Like if you've ever had pasta with vodka sauce, you put vodka in the sauce, but by the time you cook it, it all evaporates. Or if you put any sort of alcohol in when you're cooking, we say it burns off or it evaporates because it leaves so quickly. Whereas we're happy that water doesn't do that, because then again, on a hot day, our oceans would all just evaporate, right? So that's what would happen if our oceans were made out of alcohol. Okay, so now, I'm going to make this smaller again, sorry. The next station, actually the last station here, has to do with pH. So you either have an acid, so pH goes from 0 to 14. And acids pretty much go from 0 to almost 7. And then a base goes from a little bit over 7 all the way to 14. Water is right in the middle at 7. What's cool is if you put an acid and a base together, they neutralize and they give you number 7, which is water. So what we're going to do is we're going to take this paper, okay, and this tests whether something's an acid or a base. So I take this paper and I'm going to dip it into vinegar. Okay, when I dip it into vinegar, it turns the sheet of paper like kind of pink. And when I put it up against the key here, it turns out that vinegar is number 2. Okay, so it's an acid. Vinegar we know is acidic, so it's a number 2. Milk of magnesia, on the other hand, if you've ever seen like an antacid medicine, what it is if you've ever had Tums, like if you've ever had spicy food, this stuff here is a base. And what's good is if you ever feel acidic and you take this medicine that's a base, so this is an 8, okay, so it's over 7, so it's an 8. If you ever take this medicine, it will neutralize the acid, right, acid and base, and it'll give you water, so it's more comfortable for you. And then lastly, if you do water, if you put this in water, it's going to be a 7. All right, so you're going to get a 7 for water, a 2 for vinegar, and an 8 for milk of magnesia or any sort of anti-acid medicine. Okay, so you can answer the graph, you can answer the questions. The main thing is when it asks in the analysis, how does the structure of water give it special properties? So the main thing about water is that it's positive and negative, and so that allows it to be really sticky. Whether that's cohesion and it sticks to itself, or it's adhesion and it sticks to other stuff. When you watch the notes, you'll see some examples. And the last thing you need to do is you need to create your own experiment that would demonstrate some of these characteristics of life, characteristics of water. Hopefully I know you can't do this in person, but hopefully that this is a good way to see what's going on.